Hello, everyone. I will present this joint work with Cesare Kalizik and Joseph Urban. I'm Thibault Gauthier, and this has been at least 4 different papers on this work. 3 of them was with Cesare, and 1 of them was with Joseph. And I will try to present this work here. So we start with libraries. So 2 libraries, let's say. One library is from one interactive theorem prover, another library from another interactive theorem provers, and we have concepts in those libraries. And on the left side you have the list concept. On the right, for example, you have riddles, but you might not have exact match between the 2 libraries. For example, you have multiple plus on the left side and only 1 plus on the right side. So the goal is to find a good alignment between those 2 libraries. And this algorithm, let's see which libraries we are considering here. So we have here a list of 6 different libraries: Weezer, Coq, HOL4, HOL Lite, Isabelle, HOL, and Matita. And here is just a sample of all the theorems and I could gather from each of those libraries. It's not the full libraries. And we are only interested in statements like theorems and like the constants that appears and the types that appear in those theorems. And we are not interested in proofs. So we will ignore, in the rest of this talk, you can ignore proofs. We will just consider statements and figure out how to recognize which concepts are similar across the different libraries. So first I will present the general approach, general idea, then I will go into the details of the alignment algorithm, and finally I will show some applications. So the general approach is some syntactical approach where you will find different constants or concepts that have similar properties. So the first step is to find properties, let's say, such as associativity, commutativity, nilpotence, etc. And the second step is to measure the overlap between the properties of one constant or one concept and properties of another concept. So if they share a lot of properties in common, they probably are similar. And this is all statistical, so we give a score on how similar they are. So why would it work? The first thing to realize is we're not looking at definitions, and we are not trying to prove that the definitions are equivalent. So we are only doing measuring how many properties are similar, and those properties are often written in a similar way across proof assistants. And this could be also a reason why it would not work, because properties may also have a very different syntactical representation, and there is no way to recognize that they are similar. So that's advantage and disadvantages of our approach. And finally, it's statistical, means even if not all the properties are the same, you're missing some properties in one proof assistant, you still can find a probable match between 2 constants or 2 concepts. So let's go into the detail of the algorithm. So I will first say that the logical operators, we manually align them, like for, equal, implication, and so on. We recognize where they are in each library, and we say, well, this is the for all, and we should map it to the other for all in the other library. This is not strictly necessary, and the alignment algorithm can still work without this initial mapping. So now let's see how we create properties. So given one theorem in one library, this is the first theorem here saying that x plus 0 is x. We first apply some normalization. We want to have all the theorems in the same shape. So here, for example, we put the smallest left-hand side of a, since a equal b and equal is, since it doesn't matter, equal is symmetry, a equal b is the same as b equal a, then you can reorder the argument and say, put the smallest first. The same for plus, but we didn't have to do it. So we recognize which operators are commutative and associative, and we do some normalization based on that. And the final step is to ignore the name of the constants, so or the types. So we abstract over the name of the types and the constants, and we just remember in which positions they appear. It's shown by a lambda here. You can do the same with another theorem. Here we start with the theorem x equal x times 1, and x is, and 1 is written as s of 0. But here's a very nice thing you can do, is to replace this s of 0 by a single constant. And we just name it c and index by s of 0. And you also do the normalization with multiplication and equality. And you get this final theorem. And now you abstract again over all constants and types. And you realize that you get exactly the same property, modulo alpha equivalence. Then we can say that in some way it tells us that num is, well, num, which is a type of natural numbers, is similar to real numbers, and plus is similar to multiplication, and 0 is similar to s of 0. So here we could say, why not do anti-unification on the initial two theorems and figure out what's the correct anti-unification? First of all, this is expensive. You have to do it for all pairs, where here we can have just a hash table which stores a property, so it's linear versus quadratic. And second of all, it's difficult to do anti-unification modulo property, the normalization property like associativity and commutativity of all our operators. So here we took all the libraries and we took all the theorems, and for each of the theorems we constructed one or sometimes two properties out of each of the theorem, depending on if we apply this concept of subterm conceptualization. We replace some subterm by a constant, which is actually very useful. And we get this list of property for each library. So you have the 6 libraries, for example, you have 157 theorems, which are instances of the commutativity property. So the commutative property here, I've restated here, is lambda plus for x0, x1, x0 plus x1 equal x1 plus x0, as you would expect. But of course, it's abstracted over the plus, so it can be anything for the plus. So this table only shows properties of one constant. They can be properties of multiple constants and also types. So here's properties of 2 constants, for example, distributivity. So in Coq is the most common thing, and you can write it here as you would expect. x0 times x1 plus x2 equal x0 times x1 plus x0 times x2. And again, it's the name of the plus and multiplication don't matter. So now we have the properties. So now we have to find which constants have those properties across two different libraries, have the same properties across two different libraries. So we take one concept in one library, let's say it can be a type, let's say the natural numbers in one library and the natural number in another library. And we share count. The first idea is just to say what properties of natural numbers are true here and also true in the other, and count the number of properties they have in common. This is very simplistic. You can do a bit better because you can realize that a rare property is much more important than a common property. For example, for plus, like having the property of being commutative is not very distinctive. Like many constants have this property. So if two constants are commutative, it really doesn't mean they are the same. So we should give a stronger score or to properties that are rare. That's the second idea. And the third idea is that if you have co-occurring matches, they should influence each other. And I will tell you this how this works in our original example. For example, our original example, you have three derived matches. Num is similar to real, plus is similar to multiplication, and 0 is similar to successor of 0. But if we assume wrongly that 0 is similar to successor of 0, or approximately, we should also give a higher weight to plus is similar to multiplication. They are interdependent. The more I trust that 0 is 1, the more I should trust that plus is multiplication. So it will give another example. Here it's between Isabelle Hall and Miser. So we have that 0 is similar to 0, natural number is similar to natural number, but 0 is also similar to the empty set, and less is similar to less, but less is also similar to inclusion. So which one do you choose? So yeah, there are multiple possible mappings, and more importantly, the same idea applies as before. If you think that 0 is similar to the empty set, then it should make you believe that the natural number are the same as sets, so or similar to sets. But eventually, we want to find maybe the exact match or the black part. So we want to say, oh, now I know that, let's say, less is similar to less in the other library, then that should influence my choice, and I should say that the natural number are similar to natural number, and then that would prevent me from choosing that the natural number are similar to sets. So once you have this graph of interrelated matches, you can try to figure out scores in a more careful way. And I would say what the strength of the match is dependent on the number of property these two co-occurs in, and also is dependent on how rare those properties are. So now we start with score for those matches. So let's say we give a score of, let's say, arbitrary 1 for each matches. And I will ask you to imagine what will happen is, let's imagine that the size of the bubble is the confidence you have in the match. So the bubble will grow and decrease depending on how confident you will become after iterating some message passing across this graph. So saying, oh, I know that not is not, so I should know that less is less. So gradually, as an iterative process, then this iterative process converges, and you can prove that it converges depending on the formula you choose. And it converges to a score, and then this is the score you give to the matches. And there are potential self-loops because you can say that the pair co-occurs with itself. And also it's important if you're to consider properties that only are mentioning one constant. So now we have two libraries, and we know a score. For each pair, we have a score that tells us how similar two constants are, or concepts are. Could be two types also. But this does not give us a one-to-one mapping. It's a many-to-many mapping. You have many potential match for natural numbers, for example. There are many potential matches in Coq. You have like maybe 6 different representation of natural numbers. So maybe we want to only focus on having a one-to-one mapping because it makes our life easier for our application later. So how to construct this coherent mapping, one-to-one mapping? So the first idea is to employ a greedy strategy. You take the best match, and then you look at which constants appear in this best match. Let's say the best match is plus with plus. Then you disallow competing match. So any matches that mention plus is removed from the computation. And you also assume that you have already this match, and then you recompute the scores using the same algorithm. Second idea is to, given that you have matched one constant with another constant, you should also match the types of that constant with the types of the other constant. So say I match the 0 of integer with the 0 reals, then I should match the integer with the reals. And finally, an important part is sometimes you have ambiguous match, like we've seen before. And the idea is to delay those matches to measure some, if you have multiple matches, you give a lower score to the match because you're not very confident in which direction, and you prefer to select matches that have no competing or competing matches with very low score, like a very distinct match. So we have tried this between all pairs of 6 libraries. So you take one library and another library, and you apply this algorithm to get a one-to-one mapping. And then we look through the one-to-one mappings, and we've looked at what position we get something that is clearly wrong or approximate. So for all for one holite, it works very well because they are very similar, and we only get something wrong at the 227 mapping, and we have that the type of x real number is a type of complex numbers, which is not true. And but for example, Isabel and Miser, it doesn't work as well, and we get already a wrong match very early. For example, and for Coq and HOL4, we get a wrong match very early, but if you ignore this, it's actually not that bad, and we get a lot of good matches even after the first wrong match, because sometimes the first wrong match propagates and sometimes it doesn't really, depending on how important this match is. So we have all those mappings. Now we will look at the applications the first one is not really an application. It's some it's something you can do with the mapping between two libraries. Let's say because Isabelle and Miser somehow you don't manage to map them nicely, you don't find a mapping, but you could go through another theorem prover and find a mapping through that theorem prover. Here I say, well, if you look at the direct mapping between this subterm less real and less of 0 in Miser, the direct mapping gives you a score of 0. But if you look at the transitive mapping, meaning if you look at the score you get if you map whole with Isabelle with whole light and Miser with whole light for this constant, you can multiply the two scores and you get the transitive mapping of 0.5. Means there are some properties that tells you that these are similar and are similar, but there are no properties that tell you directly that those two are similar. So you can get an extra mappings this way. Same is true for other examples here for real and times complex. That's a nice thing you can do to increase the matches. Get matches even if you don't have any. The second application is that is really maybe what we had in mind at the beginning is you start with some conjecture and you want to prove it, but you realize this conjecture maybe after mapping it to another library it already exists, and you can use the relevant lemmas, find the lemmas that were used to prove it, translate those lemma back, and try to prove it using Hammer. But also, it's possible that after translation, the conjecture does not exist. So in this case, you can still do some prediction just by using a predictor saying what relevant lemmas should be useful, and then translate those relevant lemma back and try to prove the conjecture. Using those strategies, starting with, let's say we start knowing that the full library of HOL light, and we want to try to prove theorems in HOL4, we are able to, if you just use the Hammer inside one library, you get 40%, 43%. But if you use external advice, you can get until 50%. If you combine the two scores together, you get 60%, 2% of theorems that you can reprove. And the same is true for whole light advice by whole 4. But of course, this works because the two libraries are very similar, so it's true that you can somehow port the proofs from one theorem. Port the proofs, I mean, in the sense of just porting which lemmas are useful for which theorems. The last application is that you can do this reasoning inside one library. So you have a conjecture you made in one domain, and you realize it's true in another domain, and there is a proof there. So you look at the relevant lemmas, and now you translate them back using the mapping. And then you try to prove the conjecture. For example, in Miser, we first align Miser with itself, and we find some mappings. Of course, we find the identity mapping, but we'll also find things like continuous is similar to Lipschitzian. So every theorems about continuous, maybe we can consider them theorems about Lipschitzian, and we can make conjectures, and we can prove them. Here we constructed 75 conjecture, and we proved 6 of them. And you can do this for other mappings, and this is some kind of reasoning by analogy. Finally, I want to conclude by recapitulating all the points. So what we have done is we have looked at 6 different libraries, and we have used a statistical and syntactical approach to match concepts between the libraries. And it works even if the concepts have different definitions, even if the concepts are not exactly equivalent, and even if the concepts have a slightly different syntax. And this is an important point. Like, sometimes you have one represented as s of 0, sometimes it's just a constant, or sometimes you have power of real, and sometimes it's just one. You have a type argument, and sometimes you just have one constant. And this is done through subterm conceptualization. So we choose subterms, and we usually frequent subterms, and we make one constant out of them. And this is an efficient mapping. And you get similitude scores. And then we construct one-to-one mappings by enforcing coherence between the matches of the matches. And finally, such mappings can be used to prove theorems using advice from another library, or port theorems from one library to another, or you can even use the approximate mappings to make conjectures via analogy. So even if in the first case you want more exact mappings to port theorems from one library to another, in the second case you want more approximate mappings. So both kind are good. Thank you for listening.